Today we are fortunate to have Professor John Hassler here to give us this lecture. And the message of today wants to be a message of hope, especially for the young people in the audience. And I believe that despite critical challenges, leveraging science, engineering, and governance, we as a society can avoid a climate catastrophe. Professor John Hassler is going to offer us an economic science perspective on solar geoengineering. And before Professor Hassler's lectures, I will give a very short introduction to the topic of solar geoengineering. So solar geoengineering is a technology, is a tool to modify the amount of solar radiation that is reflected by planet Earth. And by using solar geoengineering in synergy with other climate change mitigation techniques, primarily the reduction of greenhouse gases, as well as the carbon dioxide removal, by using also solar geoengineering could cap the maximum temperature that the climate change is causing. There are mainly three types of solar geoengineering techniques. One is acting at low altitude in the atmosphere. Another one is acting higher in the atmosphere. And the third one is space-based, is acting from space. Starting from the lower one is called marine cloud brightening. And the main idea of this technology, which is the only one that has been tested locally in Australia, the idea is to increase the reflectivity of the low clouds across the ocean, on top of the oceans. And there is a naturally occurring analogy, where a human-driven analogy, but is the trail that are left by vessels, marine vessels, in specific meteorological conditions. A second technique is called stratospheric aerosol injection, and the idea here is to insert in the stratosphere, that is the second layer of the atmosphere between 10 and 25 kilometers of altitude approximately, to insert an aerosol of sulfur dioxide in order to provoke a increased reflection of the solar radiation that reaches the surface of the Earth. The natural analogy in this case is the one of the major volcanic eruptions, like the Mount Pinatubo in the Philippines that is depicted in this picture. A third technology, that is the space-based one, is called the planetary sunshade. Here the idea is to insert in an orbit that is between the Earth and the Sun a very large space systems that we call a planetary sunshade, or also called a solar sail, or a multitude of solar sail. And the idea here is simple to get, is to create basically a shadow, so to speak, between on the Earth. Actually is not exactly visible, but basically is a reduction of the sunlight. And here the analogy, the natural analogy, in addition to the moon eclipse, but will be much less invasive than that. A more correct analogy would be the one of the passages of the Venus and Mercury over the Sun that happens extremely rarely. And in the picture on the right-hand side there is the passage of Venus in front of the sun disk. So imagine to have a disk that is constantly there, that planetary sunshade, will reduce the sunlight that reaches the Earth of a very small percentage, say about 1%. But that could be enough to cap, as we said, the increase in temperature. I believe that, and there are many people that believe that this technology versus the other tools provide key advantages. First of all, it will be reversible. It will not coupled directly with the atmosphere. That is a very complex, of course, system. And it will provide a global effect. So in synthesis, solar geoengineering holds the promise and the hope to provide society with a tool to mitigate climate change temperature increase. It must complement other techniques, in particular the reduction of greenhouse gases. And space-based solar engineering offers key potential advantages with respect to the other two major techniques that have been proposed. I would like to welcome at this point Professor John Hasler, and I will introduce him first of all. Dr. John Hasler is a professor of economics at the Institute for International Economic Studies of Stockholm University in Sweden. He received his PhD in economics from MIT in 1994. His research has been focusing on dynamic public finance, social mobility, growth, and climate change. Since 2009, Professor Hasler is a member of the Committee for the Nobel Prize in Economic Sciences of the Royal Swedish Academy of Science and the Royal Swedish Academy of Engineering. He was an advisor to the Swedish Ministry of Finance, and he is a member of the Economic Council of the Minister of Finance. Professor John Hasler's lecture today is titled Insurance Against Climate Change. Please, Professor Hasler.
Thank you, Marcello. Thank you very much for the long introduction. I realize that I've become pretty old, and also that it was 30 years since I took my PhD, pretty much exactly. I'm very honored to be here to speak to you about my views on what to do about climate change. For many of the things that I'm going to talk about, there are experts here that know much more than I do, for sure. But nevertheless, I think that it is important for social scientists and engineers and natural scientists to engage in contacts about this issue. We are not going to be able to solve the issue of climate change without the contributions of natural scientists, engineers, and social scientists. So one of the rewarding things of the research that I've been doing for now approximately 15 years in this area is that I get to speak to natural scientists, and that's very interesting and nice. So what I have been doing myself in my research is, together with other economists and with the input of, in particular, people from meteorological sciences, construct global, what is called integrated assessment models. And these combine a model of the economy, which then has to be a very long-run model, because climate change is a very slowly and long-run phenomenon. It has to be global, and we combine that model with the model of how the climate evolves and how carbon circulates between different reservoirs. And the purpose of these models is to examine the consequences of different assumptions about policies, about how damaging climate change is, and how sensitive climate is to emissions, to provide an idea of what can be done and what perhaps also what should be done. So when I speak about these issues, I always start with talking about natural science, and in particular the greenhouse effect. And I think that everyone, also social scientists that work in this area, need to have some basic understanding of the natural science. And the fundamental reason for why we are thinking about these issues is that greenhouse gases affect what we often call the energy balance or the energy budget of Earth. And this energy balance is an account of the incoming energy flow from the sun to Earth and the outgoing energy flow to space. And for the climate to be stable, these energy flows has to be balanced to each other. The incoming energy flow is, of course, in the form of visible sunlight mostly, and a third of it is directly reflected away, but the rest comes to us and makes it fairly warm here. The outgoing energy flow, apart from the share that is reflected away from bright surfaces of Earth, is mostly in the form of heat radiation. So electromagnetic radiation with a lower frequency. And what happens when you have greenhouse gases in the atmosphere is that this outflow from the surface of heat radiation, infrared, is blocked. And that has been known for a very long time, since the early 1800s, that greenhouse gases has this effect. I often make the analogy with going to a bar when I talk about greenhouse gases. So, you know, if you go to a bar and there is a band playing, say there is with a strong amplifiers, so it's powerful music, and you have a guitar in the band and you have a bass guitar also, a bass. Then I guess everyone has noticed that if the bass player takes a note, then things starts to vibrate. Cutlery, cups and so on starts to vibrate. But when the guitar is playing equally loud, nothing is vibrating. And why is this? Well, it is because these objects, the knives and forks and cups and so on, have the inherent ability to vibrate in sync with the bass tone from the guitar, not from the high-pitched guitar sounds. And here it's similar, that greenhouse gas molecules can vibrate in a frequency that's aligned with infrared radiation, but not with sunlight. And that implies that if you were to be out in space and watching Earth with a heat camera that only can see heat radiation, you couldn't see the ground. You could see something down to maybe 5,000 meters. And this means that the heat from Earth, from the ground, needs to be transported up in some other way than through radiation. And mostly it is because in the form of convection, that warm air rises until the heat has come up to a level that has a concentration of greenhouse gases that is so low that heat can disappear in the form of electromagnetic radiation. And this is very much similar to what happens if you lie in your bed and freeze. Heat is streaming away from your body. But if you put a blanket on top of you, heat cannot leave your body directly in the form of heat radiation. It has to be transported up to the surface of the blanket, and then it can be radiated out. And what happens is then that it gets warmer below the blanket. So the greenhouse gases works exactly like a blanket, and what happens when we put more of CO2 in the atmosphere is that this blanket becomes a little thicker, and that is the fundamental problem. So this has been known for a quite long time, and actually the first person who quantified the effect of having more CO2 in the atmosphere was a Swede, Svante Arrhenius, who did this in the late 1800s. And there is a nice paper actually that's perfectly readable, even to a social scientist still, about these things from 1896. So I recommend that for reading if you want. So he quantified this, and it turns out that his quantifications are not that far off today, although we, of course, know much more about these things than what was known then. As a little anecdote, you can note that Svante Arrhenius, he thought of this as something that we could use to our benefit. So he was worried about Earth transiting into an ice age. And then he thought that if we massively can emit CO2, we can prevent the consequences of an ice age. But now his results are used for other purposes. So we had the first real climate scientist in Sweden. We also had the first climate denier, actually. And that's related to the Nobel Prize. So in the physics committee, there was a person, Knut Ångström. Ångström, you know, the small measurement unit, the son of that guy. He was in the physics Nobel committee. And he argued that this idea of CO2 being able to change the climate is rubbish. So because of that, perhaps at least, Arrhenius didn't get the Nobel Prize for these things. So we had the first climate scientist and the first climate denier in Sweden, which is, I think, a little funny. Okay, so this, what I've said so far, is pretty straightforward and simple. In reality, of course, things are much more complicated. We have to take into account, as Marcelo said, cloud formation, for example. We have to take into account how air and streams, water streams, transport energy around Earth and so on. So it's a very complicated system. And when we think about the consequences of emitting CO2, we also need to think about the transportation of carbon between different reservoirs. The whole thing then, of course, becomes highly complicated. But surprisingly, nevertheless, it's been fairly recently shown, since maybe 20 years or so, that the total effect, or the relation between CO2, carbon emissions, CO2 emissions, and the increase in the global mean temperature is approximately linear. And more specifically, the linear relation applies to the over time cumulative amount of emitted CO2. So how much we have emitted of CO2 since we started 150 years ago. That stock is approximately proportional. The temperature in the global mean average, global mean temperature is approximately proportional to that, in the short and in the long. And that result implies a couple of immediate consequences. First is that we cannot continue to emit. As long as we emit CO2, we continue to accumulate emissions, and that leads to an increase in the continued increase in the global mean temperature. So we eventually, it's clear that we have to stop emitting CO2. And another implication is that when we stop emitting CO2, then of course the historically cumulative amount of CO2 remains constant, and thus also the temperature, probably for hundreds of years. So this is a graph showing this relation, and on the x-axis here we have cumulative CO2 emissions since 1850, and on the y-axis we have the increase in the global mean temperature relative to the starting point 150 years or so ago. And here we see that to the left of the point 2400 on the x-axis, to the left of that, that's data, observations. And we see, and you see a jagged curve, and that's the temperature, then as a function of the cumulative amount of emissions. And of course, the temperature is jagged. It doesn't, it moves for other reasons than CO2 concentrations from year to year. But we see a clear linear tendency. To the right of 2400, that's various simulations from Earth models that take into account carbon circulation and climate change. And you see that these lines are also fairly linear, keeping this proportionality relation. On the other hand, we can see that the lines are not parallel, they fan out. And this is due to the fact that although these models agree on the linearity between cumulative amounts of CO2 emissions and climate change, they don't agree about the sensitivity. They have different slopes, to say that. And this uncertainty is very important when you talk about policy, what to do about things. And I'm going to emphasize that it's kind of the uncertainty about the consequences of emitting that requires a particular type of policies. So what IPCC, the UN Climate Panel, says is that there is a lot of uncertainty. I've already spoken, I'm going to come back to it, to the slope coefficient there. But you can see that they also claim that the likely uncertainty interval about how much global warming we have caused so far is between 0.8 and 1.3 degrees. IPCC also says that likely should be interpreted as a 2/3 confidence interval. So we can, with that reasoning and with 1/3 probability, we can be outside the interval. I think that one shouldn't take these statements about probability too seriously, but it's clearly an indication that, that can be captured by the word likely. But there is no randomness. It's not like a roulette where you can actually define objective probabilities, and that's something that I'm going to come back to. One of the things that produce this uncertainty is the uncertain cooling effect from aerosols. So aerosols that we emit, particularly when we burn fossil fuel, affect cloud formation, and they also have other effects. Most likely, this is going to induce a cooling effect, but we don't know the strength of it. IPCC says that the cooling effect is between 0 and 0.8 degrees currently. This is a pretty temporary thing. So when we have come to a situation where we don't burn fossil fuel anymore, most of this is going to disappear quickly. And then, of course, if it turns out that the cooling effect was 0.8 and that disappears quickly, that's a substantial problem. But we don't really know where we are in this interval. And note that also this is a likely interval, so it can be both stronger and weaker cooling effects than this. So the slope coefficient in the previous graph that I talked about, the relation between cumulative CO2 emissions and temperature, also there the IPCC states a likely confidence interval, which is from 0.27 to 0.63 degrees per 1,000 billion gigatons of CO2 per teraton of CO2. And this is a pretty wide range. As I said, we have so far emitted around 2.4 teratons of CO2. If we do that again, if we double that amount, we're going to get between 0.65 and 1.5 degrees additional warming, and that's a pretty substantial difference. Something that I'm sure that you have heard a lot of, it gets a lot of attention in media, is global tipping points, namely that at some point, perhaps this relation between emissions and temperature changes abruptly, so that the temperature goes up a lot. And IPCC says that they think that that is highly unlikely, and neither in the data nor obviously not in the data, nor in the models, but you cannot logically rule it out. So when it comes to the consequences for humans of climate change, our research have shown that the uncertainty is equally large. It's very difficult to know exactly how difficult it's going to be to adapt to climate change. My colleagues in the meteorology department, when I ask them what they are most worried about, they often say that, well, maybe it is that if we get, say, 3 degrees of warming towards the end of the century, then heat waves at highly densely populated areas of India, heat waves that occur maybe every decade or so and can continue for a couple of weeks. During those, it's going to be so warm, so it's physiologically impossible to be outdoors more than an hour or so. And this is because it's not only hot, it's also humid. So these are conditions that we haven't seen before in human history. What are the consequences of this? Well, certainly that's going to depend on where India is in terms of economic and technological development towards the end of the century. If they have an ample supply of energy, everyone has air conditioners, agriculture is done with tractors that you sit inside and have air conditioned, then this is bad, but it's not a catastrophe. But if they haven't come to that point, then these situations would be really, really catastrophic. It's hard to know where India is going to be 75 years from now, and there is no objective probabilities either. So clearly, we cannot rule out very bad things happening, although many of the studies that we see point to relatively undramatic consequences of climate change, at least in the aggregate. For particular regions, for particular people, it's certainly worse, and it's also worrisome that it's mostly areas of the world where people have less of resources to deal with climate change that are most adversely affected. Economists and philosophers call the kind of uncertainty that we are facing Knightian. And with Knightian uncertainty, we mean uncertainty that do not have any objective probabilities associated with them. And given that, our economists' traditional tools, namely cost-benefit analysis, is not very convincing. Cost-benefit analysis implies that you see what kind of possibilities are, and you assign probabilities to them, and then you can calculate an expected cost, and you say that that's how much it's worth to do something about climate change. In my thesis from MIT, I did a lot of analysis of investment and under uncertainty, and a clear result from that analysis is that often in a situation like this, wait and see is the right thing to do. So wait and see is a good strategy if you are about to make an important decision and don't really know what to do. But this requires that you actually see, that you, by waiting, you get more information. And I argue that that's not very likely. These uncertainties that I've spoken about do not seem to have a clear downward trend. Many of the natural science uncertainty intervals that I've spoken about have been approximately as wide since IPCC started with its reports 30 years ago. So that they suddenly going to shrink, and we know, for example, the sensitivity of climate change to emissions, that's very unlikely. Same thing with the consequences of climate change for humans, that we're not going to learn that in the near future. And with near future here, I mean decades. It's also the case that while waiting, we continue to accumulate. So things get potentially worse if we wait. So wait and see is not a good strategy. Could we then, on the other hand, find a robust policy? And with a robust policy, I mean a policy that we're not going to regret much, even if it turns out not to be the correct one. Such a policy can also be described as an insurance policy, an insurance against bad outcomes. And here we have used our integrated assessment model to show that there is such a policy. And the baseline policy that is robust is a slow transition to climate neutrality over, say, 30 years. And here, a carbon tax or a price on emissions is a potent policy tool. So I argue that we can reach climate neutrality globally 2050 at a relatively small cost. This is a curve. This is a figure that comes from a study by IMF that shows the cumulative costs in terms of lost GDP by a transition to climate neutrality by 2050. That's based on pricing of CO2 emissions. And you see here that most of the curves, are around zero. So it's not really costly if you do it in the right way. Russia and the OPEC, the red and the blue line here, they lose. I guess OPEC can take it, and Russia, I guess, have bigger problems than this to worry about. Our research shows that an ambitious climate policy is robust. It offers cheap insurance, and this curve also illustrates that. So here we have looked at the potential for regrets. So what we did is that we used our model to look at the consequences of two types of policy mistakes. One is to have an ambitious climate policy that takes us to climate neutrality by 2050, but it turns out later that that was too over-ambitious. We didn't really need to do it. So we are in the kind of the other end of the uncertainty intervals that I've been talking about. Climate isn't that sensitive to emissions, and we can relatively easily adapt. So then we realized that we did too much, or at least too early. And the red curve here is the cost of that policy mistake. And what we see is that that's relatively low. The other one, hoping for the best and thinking that we are probably in the other end, the low end of the uncertain intervals, but it induce a policy that is right then, which later on turns to be wrong. The consequences of that policy mistake is the black curve here. And here, this is a relatively conservative description in the sense that I don't take into account the possibility of tipping points and so on. Another thing that comes out of our analysis that we really have to kind of do it everywhere in the world. So if we used our model to look at the consequences if some regions in the world don't participate and the others have to make up for it. And what we find is that if India and Africa don't participate and the rest of us, everyone, China, the US and Europe, try to account for that, we need to have 5 times higher price on emissions, and that's going to be very tough. If China doesn't participate, it's actually physically impossible to undo that. But so if they do a little bit, nevertheless, the rest of us needs to do 20 times as much, and that's not going to work. So this is a talk about sunshades, and if you are keen on me coming to them, I'm going to come to them soon. But first I want to say a thing that also I think Marcella alluded to, that I think there are reasons to be optimistic. And one of the things that make me optimistic is that you see a lot of policy action taking place now. And in particular, the Fit for 55 agreement that was done in EU last spring, which, as you probably know, implies a tougher EU ETS 1. So EU ETS 1 is an emission trading system that ensures that firms in that system cannot emit more than the number of emission allowances that are distributed to the market. And they cover around half of emissions. It's power generation, it's heavy industry, it's flying within the union, sea transport within the union. Around half of CO2 emissions are covered by that system. And now the phase out of the distribution of new emission allowances is going to go much faster. It's going to come a new emission trading system from 2027 that covers basically the rest of CO2 emissions, particularly heating and transportation. The benefit of these systems is that you get perfect control of the amount of CO2 emissions. They're not going to be more nor less than the number of emission allowances that are distributed. So we get practically full control over all future CO2 emissions until we don't distribute any emission allowances anymore. And you can calculate how much CO2 emissions is going to come out then in the Union until we become climate neutral. And this is not the target, it's not the goal, it's actually the consequences of these systems that we have now introduced. And it's going to be 35 gigatons that we emit CO2 over the entire future, unless these systems are thrown overboard. That's around 75 tons per EU citizen. And then you can notice that if everyone does the same, 75 tons per citizen, and then I'm actually including emissions that have already taken place, the calculation starts at 2020. 75 tons per capita in the world, multiplied by 8 billion people, that's 600 gigatons, and that's not far above the carbon budget for 1.5 degrees that IPCC has stated, and much below the one for 2 degrees. So when it comes to limiting CO2 emissions, EU is doing enough. So these are the conclusions then, before I come to the sunshades, that a transition to climate neutrality is a good insurance against the uncertainties of climate change. It can prove to be very important for us and future generations, and if not, it doesn't have to be very costly. We won't regret very much that we, towards the middle of this century, are climate neutral. We are really doing what's required, and the rest of the world needs to get on board. But the problem with this analysis is that there are a number of problems with this analysis. First is that climate sensitivity might be substantially higher than what we expect. It could be the case that the transition to climate neutrality to the middle of the century is not enough. Global tipping points in the climate are unlikely, but cannot be ruled out fully. Can also turn out that adapting to climate change is much tougher than kind of the median estimates. And of course, everyone realizes that international negotiations might break down. Maybe we're not going to be able to get an international deal so that everyone participates in that. So for that, I think we need another insurance. We need a plan for the worst case. And the transition to climate neutrality, the current plan, is not really sufficient for that. And one thing that I think we need to put emphasis on is sunshades in space. And these are some. So one of the things is when you cooperate with natural scientists, and in particular in astrophysics, you get nice pictures. We don't have as nice pictures in social science. And one of them here is actually my co-author waving to the photographer. So Christer Fuglesang, who is my co-author on this work, was an astronaut and was the first Swede in space, actually. Here, what we and these things, and I'm talking about now, is based on his research. This is outside my area of competence. But the point here is, as Marcelo said, that what we could do is to place sunshades at what is called the Lagrange point between Sun and Earth. So the Lagrange points are, by the way, I passed the Lagrange street yesterday, and it's very nice to hear his name also there. So Lagrange points are points in space where the gravity of the Sun and space, Sun and Earth, and I guess also the Moon, approximately balance. So in principle, if you put the thing in the Lagrange point, it's going to stay there. It's unstable, so just some deviations will imply that it goes away. But nevertheless, if you can control these deviations, things will stay at the Lagrange point. And there are several Lagrange points, of course, and here the one that is between the Sun and Earth is the one where we should put these sunshades. And the distance is approximately 1% of the distance to the sun. So something, what is it, like 4 or 5 times the distance to the moon. A benefit with it is that these shades would always be in zenith, so it would always be kind of in the on the sun, as the picture by Marcello showed. So I guess you could see it with a binocular, like a sunspot or something like that, but otherwise it would not be visible. Here, which also Marcello said, we would like to cover around 1% perhaps of the inflow. And where does that come from? Well, 1% of the inflow, if we can cover that, so basically cover 1% of the area of the visible area of the sun. We can do that. That neutralizes the greenhouse effect over the doubling of the CO2 concentration. We are not there yet. We have increased the CO2 concentration in the atmosphere by around 50%. So if we continue a bit and come up to a doubling, 1% of shading off sunlight would neutralize that. 2% would neutralize a quadrupling. And why a quadrupling? Well, it's because the greenhouse effect is logarithmic in the CO2 concentration, so it's not linear. The idea here is to launch these parasols or sunshades into Earth orbit with rockets, and then let them sail on the solar radiation pressure. And the solar radiation pressure can be used actually to sail by affecting the speed that the sails go around, or shades go around the sun. So if you can break that rotation around sun, they're going to fall towards the sun to that place. And this is a technology that, of course, is to some extent yet to develop, but there are already actual sun sails in space. Clearly, 1% doesn't sound much, but it's a big area. So I think it's like 6 times the area of France or something like that that needs to be covered. It should be done with small sunshades. In Christer Fuglesang's work, the idea there is to have around 500 million sunshades, each the size of a football field approximately, 7,000 square meters or something. And that they should be launched over a time span of around 20 years. How much is this going to cost? This idea has been around for quite a long time, but it used to be so expensive to launch things into space that it's, prohibitively costly. That has changed, and as I guess many know, partly because of Elon Musk's work, costs have come down substantially. In this work, we don't take Elon Musk's promises of future cost reductions really totally at face value. So we don't go as far, but we need to believe that costs are going to come down substantially also in the future. And the cost that here is assumed, to get an idea about it, you can say that it's around 5 times the current fuel cost of lifting up things into space. So with that, it's going to cost around 1.7 trillion US dollars to launch things up into orbit from where it can sail to the Lagrange point. The construction of these sunshades would be almost $1 trillion too. Another costs $500 billion. So that adds to, of course, just a guesstimate, but nevertheless, an idea about kind of the total sum of $3 trillion US dollars. And actually, the first time Christer Fuglesang contacted me. He called me up and said, John, I have a thing I need to discuss with you. I've done this solar shade, sunshade project, and we come to the conclusion that it would cost something around 3 trillion. You're an economist. Is that a lot? And I told him immediately, no, that's not actually, it's a lot of zeros, but it's not very much. And to get an idea, you have to always to get comparisons, right? If to get sizes, you need to compare the size of something to something else. And one immediate thing to compare to is global GDP, which is around 100 trillion per year. So this is 3% of 1 year's GDP, which is of course a lot of money, but not if this is really necessary to do. We invest, the total investments in the world is close to 25% of GDP. So this is less than 1% of total investments that would have to go into this. So it's, as a share of global GDP, it's in the same order of magnitude as what the Americans spent on the Apollo project. And it's less than 3 years of NATO military spending. So of course it's a lot of money, but you know, if it's really necessary to do it, it's not a lot. So I would say that in the worst case scenario, where some of the things on the previous slide happens, cost is not the issue. But there are other arguments against, of course, and the major argument against, I think, is that plan A, phasing out fossil fuel, is a better plan. And if you even develop the possibility of using this as a plan B, that might reduce the effort in plan A. So maybe it reduces the possibility of phasing out fossil fuel in 30 years. I think this has to be, it has to be understood that this is a correct and relevant argument. I think of the sunshade as a plan B or as an insurance as a worst case scenario. And it is the case that all insurances have negative side effects in the sense that they reduce the incentives to to reduce other risks. That's true for all insurances. It's true for car insurances. It's true for home insurances. And economists call that moral hazard, that if you are insured, you put less effort into doing the right thing. But we also know that this fact doesn't rule out insurances in general. We have to find a balance, and sometimes, you know, this moral hazard issues is so bad, so maybe you can't have an insurance, but most of the times insurance is actually a good thing. And here I argue that if we make sure that we nevertheless put emphasis on plan A, the value of, in addition, having this insurance is very high, because plan A is not sufficient in worst case scenarios. We need something more for that. And the balance here is then that the value of that additional insurance for worst case scenario is likely higher than the moral hazard cost that is induced. But of course this needs to be discussed, but I find that pretty clear. And I also think that we have to emphasize that phasing out fossil fuel globally has to continue to be plan A. But in addition, we should plan for a worst case scenario, plan B. So that's my what I wanted to say. And my final conclusion is then that the macroeconomic and welfare consequences of climate change are probably relatively limited and manageable, in particular, at least in high and middle income countries. But there's a very large uncertainty. An ambitious climate policy, aiming for climate neutrality by 2050, is a good insurance. It's a robust policy, but it doesn't apply to the worst case scenarios. For them, we need another plan. And here, I think that we have to think of developing a plan B, or rather many different plan Bs that are executed in the worst case scenario. Probably they never have to be used, but they should be there as an additional insurance. And I think that preparations for this need to start now, and I know that people here are well on their way, and I'm happy for that. Thank you. I think we have time for some questions or comments. Marcello promised to translate if you prefer to give them in Italian. My Italian is pretty bad.
Se volete chiedere anche in italiano, traduciamo.
I'll try in English, but don't be too harsh if I do some mistakes. One question that is really far-fetched is, let's say we do some those solar sails that can block the sun. Do we have a plan already to use them for something after we maybe dealt with the CO2 problem? It's just a curiosity. There can be no plan, and I'm also okay with that.
Well, if you remember where I started, I said that climate change is a function of cumulative CO2 emissions. So as long as we don't actively take out CO2 from the atmosphere, we're going to stay at a higher temperature, and thus having the need for continuous shading off, right? But it could, of course, be that we come up with direct air capture or some other ways of sucking out CO2 from the atmosphere, and then we won't need the sunshades anymore. But as I understand it, then they will immediately just, if you know, press a button so that they are not, you know, stabilized at that area, they're going to just disappear into big space. Whether they can be used for something else, I haven't heard about that. Maybe Marcello, you know.
One proposition that I've heard of is to be used for possible mission of asteroid deflection. But that's, of course, coming with more design specification and constraints on the system, so may make the cost higher than needed.
Okay, I try in English. And why did you put the solar shade in the Lagrange point and not closer to the Earth, and probably use it for energy collection, beaming down microwaves to the Earth, and so getting another use of the solar shade?
Yeah, so this is basically outside my area of expertise. So Marcello is going to tell me if I'm wrong here. But the way I understand it is that if that area is much more crowded, another disadvantage is that then, you know, if they circulate, they're not going to shade off sunlight all the time. And they're going to have you're going to be able to see a lot of these things. So there are, I think, several disadvantages of having them in orbit around Earth.
They will be very much lower in the numbers. I mean, they are close to the Earth, so that the shade will be larger.
Yeah, that's right. I don't remember. Do you have an idea, Marcello, how much smaller they would have to be then?
Not on top of my mind, but what you said is very true. They will create basically a potential of space debris problem, and basically impeding or making very difficult the utilization of the space flight region between the Earth and the Moon. So,
what's the area of the projected area of Earth? Is it 500 million square kilometers, right? And you need to shade off 2% of that because half of the time it's on the other side. So it gets pretty big anyway.
Thank you.
Good morning, Professor, and thank you for your lesson. It was a pleasure to hear you out about that. I have a question regarding the building of the sunshade. Who is going to build it? Will it be like an international cooperation, like the International Space Station, a NATO alliance building, or something else? So I'm curious about that.
Yeah, so that's an interesting issue, of course. And you know, $3 trillion US, I said, is not a lot, but you know, for individual countries, it's a lot. So you know, you have to have the economic capacity of at least EU or the US to be able to pull this off, and it's so large, so it would be pretty beneficial if we can have a bigger group of countries than just US or EU doing it. That's not only a disadvantage, actually. Of course, it complicates things, but it's also an advantage if you compare it to injection of aerosols into the atmosphere, because there the price is so low, so you know, individual countries can do it. And one of the things I'm worried about is that, you know, if India comes in the situation that I talked about, that it's so hot so you can't be outdoors, if we haven't done something about it, that situation, they're going to do this themselves. And if many different countries starts doing this, you know, in an unorganized way, that's really bad, and that is the possibility. Kind of an unorganized, multi-country competition in putting sunshades, that's not going to happen because of the costs. So you need some cooperation, and I think that's good. But the details of that is, of course, still to be done, and people like you will contribute, hopefully.
Thank you. I had a questions about the assumptions on launch costs, because if I'm not mistaken, I've seen that your assumption is about $50,000 per tons, and I wanted to ask if it's not a bit optimistic, considering that currently the demonstrated launch costs are about $2 million per tons on Falcon 9s. Well, obviously, I guess there will be some massive scale economies considering the scale of the project, but I wanted to ask if it's not a bit optimistic for an insurance project, especially. Thank you.
No, I certainly agree with that. I think Musk says that it's going to come down to 20 rather than 50, and we said that that's a bit too optimistic. Still, this is obviously optimistic, and that is one reason for why I think that one should have several kind of ideas about Plan Bs. It's clearly possible that this is not going to be able to pull off. So the point is rather that, you know, everything previously pointed to that this is obviously completely impossible because of costs. I don't think that's true anymore.
If not, we thank again Professor John Hasler for being here.
Thank you.